Hi everybody, and welcome to part 2 of chemistry. So we ended our last video basically talking about the differences between all these bonds. We had covalent bonds, we had ionic bonds, we had hydrogen bonds. So that's where we're going to pick up today. We're really going to be talking about hydrogen bonds and water. Specifically, this whole second half is basically about water. And the reason that there is so much life on our planet is because of the water that's here. So planets like Mars and stuff that don't have any water really can't sustain the kind of life that we have here on Earth, and that's really all because of water. Water does such amazing things for our planet and for every single one of our cells. So water's really, really important. So we couldn't talk about biology without talking about water. So let's get right back into it. This is where we left off from that last lecture. So this is the second part of chemistry. So let's get talking about a water molecule. Remember that inside the water molecule, right, we have that oxygen and we have two hydrogens connected to it. Well, what's happening inside the water molecule, what's holding the hydrogens to the oxygen, are covalent bonds. However, when you're sharing these electrons, remember that covalent bonds are a sharing of electrons, right? Well, oxygen is a little bit more electronegative than most other molecules, and therefore it's kind of like greedy. And so even though it's sharing with the hydrogens, it's not sharing evenly. So you can kind of think of it as like you split a pizza with a buddy, right? You guys both go in and you're like, let's split this pizza. And you have one slice and he has 7 slices. Did you share the pizza? Yeah. Did you share it evenly? No. That's what's going on with this oxygen molecule here. So you can see this end right here is considered slightly negative. So this is the oxygen side. So you can see again my big red oxygen molecule, and then I have the two little, the gray hydrogen molecules. So essentially what's happening is even though they're sharing electrons, oxygen's like, I'm going to hog some of these electrons and take more of them than you're going to get. So in this case, if you're pulling in more electrons, remember that electrons have a negative charge. So now you have more negative than positives, which is going to make this end slightly negative. Okay. Now, if you're, down some negatives, right, you don't have as many negatives as you should, then you're going to be slightly positive. And that's exactly what we can see right here with the two hydrogen molecules, or two hydrogen atoms. They are considered slightly positive. Now, this slightly negative end and this slightly positive end is actually what we call a polar molecule, or a molecule that has polarity. Okay, so anything that is polar has, a slightly different charge on either side. You can kind of think of like the poles of Earth, right? They're not different, like positive and negative, but in here they kind of are. So that's what we can see right here. This would be the slightly negative end, and up here would be the slightly positive end. So that would be considered polar or polarity. Now, this polarity is super important for what gives water all of its properties. All of the water properties come from this polarity. Okay, so all the hydrogen bonds that are going to form between these water molecules, which we're going to learn about, is all due to the polarity. So every property that we're going to be learning about water is all due to its polar, tendencies, or its polarity, as we would call it. So this would be considered a polar molecule because it has, the distribution of charges is kind of uneven. All right, so now I keep talking about these hydrogen bonds, and you're like, wait a minute, I thought they were covalent bonds. Yes. Holding this oxygen to this hydrogen right here, that is a covalent bond, a very, very strong bond. That's what's going to make this water molecule so stable, right? It's really going to be hard to break up that water molecule. Everyone's happy. Remember, oxygen has 8, hydrogens each have 2. Everybody's happy. Nobody wants to break up, right? Nobody wants to stop sharing. Now, because we have a positive end and a negative end, just like a magnet, they're going to be attracted to the opposite charge. Positive is going to be attracted to negative. Negative is going to be attracted to positive. So what we can see right here is this is the negative end, that negative end of the oxygen molecule. It's actually going to be attracted to the positive end of an adjacent water molecule. It's not the same water molecule. They're different. Okay, so what you can see right here is this negative end is actually going to be attracted to this positive end right here. And that's that dotted line that I was talking about. Remember, a solid line represents that covalent bond, that sharing of electron. But that dotted line is going to be the weaker hydrogen bond. Okay, so yes, it's still a sharing of electron, but it's not an even sharing of electrons, so therefore the bonds are kind of weak. All right, so, and again, you can see this happening with 4 of these different water molecules all being attracted to different sides of different water molecules. Okay, so this is what gives water a lot of its properties. Based on the polarity, okay, based on the uneven sharing of electrons because of oxygen, oxygen's greedy, right? You get a polar molecule. That polar molecule is going to be attracted to other polar molecules, right? So the negative end is going to be attracted to a positive end, and etc. Positive end to the negative end, and positive end to the negative end, right? They're all going to form these little connections. Those are hydrogen bonds, okay? As they kind of get connected to each other, this is what's going to give water what's called a sticky quality or cohesion. So cohesion is water sticking to other water molecules because of the polarity. Okay, if you've ever seen a waterfall, right, the water comes off and it comes off in this big, beautiful, nice arch, right? It doesn't come off and just fall flat. It doesn't come off and, fly all over the place. I mean, it does a little bit. Obviously, some of these hydrogen bonds get broken, right? They're weak bonds. But majority of the water comes off in a nice stream. Or if you've ever seen, like, if you're of age, of course, like one of those trick bartenders who can pour a mug from like way back here and you see this big spigot of water, just basically a stream of water, and it's all just one stream. It's not sloppy, it's not spilling all over the place. It's sticking to each other. That is cohesion, right? That is because of the polarity of water, they stick to one another. All right. Let's go into that. So this is going to be your first little in-class activity. Yes, you will have an in-class activity that you will actually have to do. So what I want you to do is I want you to draw me about 5 to 6 water molecules. Normally I would have you guys do this in class, but you have the PowerPoints, you have the videos, you have my examples. I just want you to draw some water molecules. You can either use the ball and stick method, or you can just use the simple, let me see if I can go back and... Okay, so you can either draw them like this, you can draw them like this, you can draw them like this, you can draw them however you want to, but I want you to stick a couple water molecules together just like we did here. Okay, so the negative end attached to the positive end via these dotted lines. Okay, so remember, these lines, these solid lines represent covalent bonds. The dotted lines in between the water molecules here and here, those are the hydrogen bonds. Okay, so you have to make sure that you guys get that correctly. So you're going to do a little drawing for me. You're going to put your name on it, and you're going to just take a picture of it and submit it to the Canvas site. So that will be your in-class participation for this chapter. I do usually do a couple of these throughout the semester, and again, that's just kind of maintaining that you guys are watching my videos and watching them from start to finish, not just kind of like, okay, I kind of saw this and I'm blowing through it. This is, again, for participation. This is something that I would do if we were in class, but we're not in class, so you're still going to get credit for being in class. All right. So again, that's what you guys are going to be doing. You're going to be drawing 5 to 6 water molecules, and you're going to be connecting them via these hydrogen bonds. All right, so let's talk about water. Let's talk about water because water on planet Earth is really, really important. In fact, planet Earth shouldn't even be called planet Earth. It should be called planet water. Because 1, it's the reason we're all here, and 2, it's like 75% of covering our planet, if not 80%. So again, really shouldn't be called Earth. It should be called water. All right, so we pretty much need water to survive. Almost every living thing on the planet needs water to survive because basically all of our cells that we're made up of are made of water. It's anywhere between 70 to 90% water of all of your cells. So since you're made up of mostly cells, guess what? You're made up of mostly water. So really important that we maintain this water concentration inside of our bodies. And again, the reason that we are such a diverse planet is because we have so much water. And therefore we can allow all of these different little ecosystems, these different little microhabitats, and therefore speciation, like the different species that we have, plants, animals, etc. So this is going to be a quick little video that we're going to show you guys real quick. Hopefully it works and YouTube doesn't flag me for it. If not, click on this video and watch this video. So we're basically going to go in all of those, into more detail about all of those things that we just learned about in this video. So all of those properties that we learned about that water is so good at, that's what we're going to talk about right now. So first of all, there's 4 really amazing properties to water. So water is just awesome. First of all, it's cohesive. Remember we talked about the stickiness of water. Okay, so water sticks to other, water molecules. This is what's going to allow that water to get from the roots of, say, a tree all the way up to, say, the redwood top, the tippy tops of the redwoods. So those leaves need water. They don't absorb water from up there. They absorb water from the roots. And therefore, when you create that negative pressure, it actually sucks water all the way up that tree trunk to the very, very tipsy tops of the canopy. All because of the cohesion of water, because they're sticking to one another. All it takes is a little evaporation at the top, and you're going to be able to pull water all the way up, which is super cool. The ability of water to moderate temperature. Again, there's a reason that we sweat. That helps us absorb that heat and cool us off. There's a reason it doesn't usually snow by the beach. Okay, that's because water is not only absorbing the heat in the summertime, but it's releasing the heat in the wintertime to maintain kind of stable conditions near the ocean. It's never 120 and it's never negative 12. Usually, of course, some beaches and some places, especially up north, get really cold, and yes, those do freeze over, but majority of the time, right? Say, think here in California, right? You can go to Big Bear and have snow, but you go to the beach and it's like 70 degrees. Also in the summertime and wintertime, it's usually about 70 degrees near the beach. The biological significance of ice floating. It's not just to look cute in your drink, right? Or to cool you off. The fact that ice floats, it creates so many other opportunities for animals and plants and stuff like that to survive during certain periods of time. It's just amazing. And finally, the versatility of water as a solvent. Water is known as the universal solvent, and that's because it's really good at dissolving like everything. And that's important. So we're going to learn about all of these right now. So let's talk about cohesion again, that stickiness of water, right? Water sticking to other water molecules because of the polarity of the water. I'm going to say this again and again and again. Water is polar, people. Okay, so water is polar. That uneven sharing of electrons by oxygen, hogging those electrons, creates that polarity. That polarity creates a charge on one side, slightly negative on one end, slightly positive on the other. Those positives and negatives are going to line up. They're going to attach to each other just like magnets, and that's going to create that cohesion, right? So that cohesion is super, super important. All right, so another thing that this cohesion does is it creates something called surface tension. Now, surface tension kind of creates like a sticky film on the top of the water. So this can actually be, you can do this experiment at home, which is actually pretty cool. If you take a penny and you slowly start to drop single drops one by one onto a penny, what you form is like this bubble, and eventually it'll actually like hang over the penny, essentially defying gravity. And you're like, how is that possible? It's possible because of this sticky surface tension. It's like I said, almost like a film on top of the layer of water that kind of creates like this protective boundary. And this is how things like creepy crawly bugs can actually walk across water. Because this surface tension, this sticky layer, is essentially these hydrogen bonds that just haven't been broken. So as he kind of balances on these hydrogen bonds, he's not putting enough pressure to actually break them. He's kind of just sitting on these water molecules. This is really cool, and we actually see a lot of marine organisms that do this. They kind of increase their surface area so that they sit on top of these water molecules without actually sinking because they don't break these bonds. Super cool stuff. So again, high surface tension because of this again, cohesion factor, which was due to polarity. All right, next up is the high heat capacity. So a high heat capacity essentially is how much heat water can absorb before it actually changes states. So if you've ever tried to boil water, you know exactly what this is. You might not have known what it was called, but you know what this is. Essentially, it takes forever to boil water, right? And that's because you're adding heat and 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 heat, and nothing's happening. That's because of the heat capacity of water. Water can absorb so much heat before it actually starts to change temperature. This is actually what moderates the temperature by the beach. Okay, so that's what keeps it cool during the summer and warm during the winter, because again, it absorbs so much of that heat energy, and then during the wintertime slowly releases that heat energy. Okay, so it's actually moderating the temperature, and here on planet Earth, moderates our temperature. So our temperatures would be way out of control and way more drastically different Even in a single day, if it wasn't for as much water as we have, kind of maintaining our planet's temperature, which is super cool because I don't want it to go from 40 degrees to 120 in a single day. That would be hard to dress for, right? So thanks to this high heat capacity of water, again, it does take a lot of energy to boil that water, right? But it helps kind of moderate our temperatures on our planet, which is really, really cool. So yes, because of these hydrogen bonds, again, because of the polarity, right, they're still bonded. So you have to add heat and heat and heat and heat and heat and heat and heat before you can actually break that bond. So first you have to actually disrupt the hydrogen bonds between the water molecules, and then what's even harder to do is you actually have to disrupt those covalent bonds inside the water molecule. And those ones are the ones that are really hard to disrupt because those are the ones like, man, I'm stuck, I'm not going anywhere. So again, it takes a lot to actually get that water molecule separated from the hydrogen bonds and then, heaven forbid, separated from itself to create things like atmospheric, water vapor to like boil it and like actually get it to evaporate. Ton of heat for that. Now, there's also another thing called evaporative cooling. So when you are working out and at the gym and you're lifting weights, right, you start to break a sweat. That's because as you're moving around, you're creating heat, right? And you're creating metabolic heat as well. So not just physical heat, friction heat, but also metabolic heat as well. And so for your body to cool itself, to maintain that 98.7, because remember homeostasis, we want to maintain nice, healthy levels. What we do is we actually kind of sweat out this layer of water. This layer of water then absorbs all the heat that our muscles are giving off. So then again, it takes a lot of heat to change the water, to affect the water, to really change the temperature of the water at all. So now your body is pumping out a ton of heat, and the water's like, all right, I can absorb this. I'm just going to take all this in and not even change temperatures very much. So again, you're cooling yourself down by basking yourself in this layer of water, because that layer of water is absorbing all the heat from you, and therefore you cool down, hence evaporative cooling. So you're going to thank your homeostasis mechanisms for actually cooling you off next time you go to the gym or go for a run. Okay, so let's move on and start talking about the biological importance of ice floating. So yes, ice does float. If you've ever had a drink with ice in it, you know this, but you probably don't know why. So now we're going to talk about why and why it's important. So first off, when you are in liquid water state of matter, essentially what's happening, and this is true of gas too, gas and liquid, these molecules are floating around constantly, right? They're constantly floating around. In the air, they're just spread out farther. In the water, they're a little bit more compact, but they're still moving around. So if you set that glass of water down and you don't touch it for 100 years, guess what? Those water molecules still moving around. Because as they move around, they're going to bump into each other. And say, what if you have two positive ends bump into each other? They're going to repel. But then two negatives are going to hit each other and repel, and then two... So they're constantly repelling off and moving around. So when you're moving around, you're jostling around, you can actually be a little bit closer together, because it's kind of like, oh, I bumped into you, now I bumped into you. We're all just kind of bumping into each other. But as these molecules start to solidify, meaning as they start to become ice, what happens is they actually freeze into place. But remember, positive ends and negative ends don't want to be near each other. So what they do is they freeze in place as far away from another one as they possibly could get. Okay, the negatives are as far away from another negative as they could possibly get. The positives are as far away from another positive as they could possibly get. Okay, so what happens is instead of this very close-knit kind of jumbled group that's really tightly packed like in liquid water, when it freezes, it actually forms what's called this crystalline shape. Because they're pushing so far away from each other, then they freeze into that place. There's all this space in between these water molecules. Inside that space is usually trapped air. So that trapped air allows these ice molecules, or these ice cubes, I suppose, now that we're cubes, right, to float, right? This is also what forms like snowflakes, those beautiful crystals and stuff like that. It's all because of the way that they freeze. The way that they freeze is all based on their polarity. Are you seeing where I'm going with this? Potential test question. What gives water all of its qualities? Polarity. What? Weird. Again, another reason to watch my videos. I like to clue you guys in on what I could potentially ask you guys for on maybe an essay question on your upcoming exam. I don't know. Okay. But anyway, so that's what we can see right here. We have this nice crystalline structure. We have that space in between. That space is going to trap the air. But not to mention, there's a lot less water molecules here in this same space than there were in this one. This is known as less dense. So density is how many things you have packed per unit area. So in this case, we have a glass right here. And let's just say our circle, just to be simplified, right? We have a circle. We have a lot more molecules here than we do here, which means that this one is more dense or more packed full than this one. So if it is more dense, it's going to be heavier. So technically that less dense water is actually going to sink down below, and you're going to get the ice, which is less dense and floating on top. So more dense, it's going to sink to the bottom. Less dense, it's going to sit on the top because this is going to be heavier than this one. So it's going to sit kind of like this against ice floating on top of the water. Now, why do we care? Well, say you live near ice, you would probably care. If the ice froze from, so say this is our water column right here, this is our ocean, and then the ice freezes up here because the air is what makes it cold. The air gets really, really cold and it freezes that top layer of water. So now you have ice floating and there's water down here. Well, if it froze from down here, what essentially you would have a huge block of ice. So you wouldn't have the water underneath the ice, you would just have solid ice. So say you're, one of these cute little fur seals, you essentially would either get frozen in that entire block or you'd have no water. You'd be stuck on the top of the ice and you'd be like, well, I have no water. All my food is down here. Even though I'm a mammal and I breathe air, my food's down here, now I starve. Not to mention, if you're one of the fish, you don't get the option to get out of the water, and therefore you would freeze and die. So what actually happens is this top layer right here protects the bottom water from freezing over, because it kind of creates a barrier. Now the cold air can't get to the water down here. The water down here is actually warmer than the cold air, so these organisms actually stay kind of warmer and protected from the cold winter environment. Crazy, right? This also happens in, say, freshwater lakes and rivers and stuff, and this is really important for any of those animals because while they're under there and they're trapped under the ice, guess who's not getting to them? Predators, right? Including us. Unless you're going ice fishing, and again, technology and humans, we drill a big hole in the ice and then we stick the thing and then we go, right? But if you're one of the natural predators, you don't get to do that, and therefore there is a time period where you're not being eaten, right? If you're one of these little fishes, you're like, man, bears can't get to us right now, so we can chill and kind of relax and maybe even start reproducing. I mean, usually it's wintertime and most things reproduce in the spring, but, they're still not getting eaten during that time period, so the populations can remain, fairly high, which is great for them. So again, biologically, super important for them. Not necessarily important for, us because we don't live underwater, but very, very biologically important for other organisms. All right, moving on. Let's talk about the differences between a solvent, a solute, and a solution. All right. So now we're going to learn that, and we saw in the video, that water is a universal solvent. So remember that a solvent is always the thing that is doing the dissolving. Okay, so just think water, solvent, water, solvent, water, solvent. Okay, so if I'm trying to make tea, right, I'm dissolving the tea in the water, essentially. So yeah, we're going to make chocolate. I don't know, that's confusing. We'll go back with tea. Okay, so the water is, again, doing the dissolving. The tea is the thing that's being dissolved. Okay, so the tea would be the solute. Another classic example, especially because it's biology, let's talk about salt water. Okay, so salt water is salt in water. Okay, so the water is doing the dissolving, the water is the solvent, the salt would be the solute, the thing you put into the water. Now, you stir it up, you stir it up, you stir it up, now you have salt water. That would be the solution. Okay, same thing with tea, like you're making iced tea. All right, you have the water, you put the tea in, now you have iced tea, that would be the solution. Okay, so the solvent, the thing that's doing the dissolving, the solute, the thing that is being dissolved, and the solution is the combination of the two, the solute and the solvent. So that would be the solution that you made, the salt water or the tea or your final product, whatever you've dissolved into said water. Okay, but water is really, really great at dissolving pretty much anything. Anything that can be dissolved will be dissolved. Now, let's look at some of our ions again. So remember that ions are anything with a charge. Okay, so we have sodium and chlorine. As soon as you actually get them together, it becomes a sodium ion and a chlorine ion, right? Because now they're charged. Sodium gave its electron to chlorine. Okay, sodium's down an electron, chlorine's up an electron. Sodium is a positive, chlorine is a negative. Okay, so now they're charged. That means they're an ion. Okay, so this would be an ionic solution. Now, any ions, anything with a charge, dissolves really easy in water. And that's because it has a charge. Guess who else has a charge? That's right, water. Polarities. It's coming back. Okay, so in this case, say I take a cube of salt. I don't know why you'd get a cube of salt, but say you have a cube of salt and you throw it in the water. So what's going to happen is these water molecules are actually going to surround the sodium and the chlorine molecule. Now, if you're sodium and you're positive, you're going to get the negative oxygen side of the water surrounding it, and that's what we can see right here. The big red ones are the oxygen. Okay, so you have the negative oxygen surrounding that sodium, the positive sodium ion. Now, you have the positive hydrogen ions surrounding the negative chlorine side. So the water molecules essentially just orient themselves however they need to point either their positive or their negative end at whichever one of these ions you're trying to dissolve. So that's what happens. The water kind of surrounds it. And then, because they have all of these positives and negatives surrounding them, sodium doesn't really rely on chlorine anymore, and vice versa. Because they have all the negatives, they have all the positives that they needed each other. But now they're surrounded by charges. They're like, well, I don't really need you anymore. I'm going to go with these guys. Okay, so that's why they kind of dissolve and they get spread out and separated when placed into actual water. Okay, so we can't talk about chemistry without talking about some kind of pH. So your pH scale is essentially a scale between acids and bases. Now the pH scale goes from 1 to 14, with 1 being a strong, strong acid and 14 being a strong, strong base. And essentially all that really means is that acids have more hydrogen ions, or those H plus ions. So if you think of a classic example of an acid like hydrochloric acid, that's actually our stomach acid. That's what helps digest food. Hydrochloric acid is HCl. The H is first because that's that hydrogen ion. Okay, there's lots of those hydrogen ions. So if we look at acidic solution here, we have more of these H pluses than we do OH minuses. Now, that's all the reverse if you're talking about a basic solution. A basic solution has a lot more hydroxide ions, or OH negative ions. And that's what we can see right here. Yes, of course, there's a couple H plus ions, but we have a lot more OHs than we do H pluses. Okay, so that would be a more basic solution. Now, if you have the same concentration of H's as OHs, now you have two H's and an O, now you have water. And that would be a neutral solution. In fact, pH 7, which is right in the middle, is considered neutral because it is pure water. So pure water is actually completely neutral. It has the same amount of OHs as H's, making it H2O. So this is actually how you can neutralize acids. If you've ever heard of that, neutralizing acids, you're trying to get it more neutral. So if you have an acid, you have a lot of H pluses. All you got to do is add some more OHs. And then it's going to shift it. Now your H's and OHs are the same. Now you are neutral. Now you're at about pH 7. Okay, so more H pluses is an acid, more OH negatives is a base. And perfectly even spread, neutral, or just water. So that's again what we can see right here. So we have a very strong base right here. This would be a pH of 14, and then we have a very strong acid right here. Now most people, and this is a common misnomer, most people are like, well, only acids can burn you, bases can't burn you, and that is not true. Okay, way down here are some severely toxic bases, right? It's not just acids that'll burn you, it's a base that'll burn you too. They're just really, really nasty and kind of crazy. So this is our pH scale, and we're basically just representing how many H pluses you have or how many OH negatives you have. Here is some examples of common household products that can be found on our pH scale. So right here we have pure water. Again, that is where the H plus ions equal the OH negative ions, right? Just slightly basic, but pretty much neutral is human blood. So our blood is just a little bit basic, but basically neutral. Very, very close to neutral. Again, so if you're close to 7, you're going to be pretty weak. So say 8 would be a weak base, right? 9 is a little stronger base, 10 is a stronger base, 14 is a really strong base. Same thing here with the acids, right? 6 is kind of a weak acid, but 1 is a very strong acid. So, speaking of acids, our urine is actually slightly acidic, right? Yes, it is slightly acidic. Black coffee and things like tomato juice are 100 times more acidic than water. And you're like, wait, what? Every number that you go up is 10 times. So if you're at a pH 7, right, and you now go to a pH 6, you're now 10 times more acidic than you were when you were pure water. So urine is 10 times more acidic than pure water, right? Black coffee is 100 times more acidic than pure water because every time it's times 10. So times 10, times 10, times 10, times 10. So technically, if we were to go all the way down here, like a soft drink is 10,000 times, right? 10 is 100 plus, 10, 100, 1,000, yeah, 10,000. 10,000 times more acidic than pure water, right? This is why things like soda are so bad for your teeth. Have you ever seen that thing where they take a tooth and they stick it in like a Coca-Cola? And like, I don't know how long later, but then it's gone? It essentially completely, like, that's how acidic soda is. You're going to think about that next time you open a Sprite or something. And then finally, 100,000 times more acidic than water would be things like lemon juice, stomach acid, and battery acid. Yeah, soda is only 10 times less acidic than battery acid. I know, really makes you think when you actually look at some of these on the pH scale. And again, when you go the opposite direction, when we're actually looking about more basic stuff, way down here we have things like household ammonia, that's for killing and cleaning, right? Bleach, again, for the killing, especially right now, the killing and the cleaning of small bacteria and viruses and stuff. And then finally, oven cleaner. So if you're cleaning out your oven, that really thick, greasy stuff with oven cleaner, yeah, it can burn you, right? Basic burns will still happen. Kind of crazy. All right, so this is a video, and I'm not going to show you this, but this is one of the videos where he actually neutralizes an acid. So he takes a very, very strong acid, and based on the, we basically have an indicator dye, so that'll change color. It'll go red if it's acidic, and it'll go blue if it's basic. And if it's green, it'll be right in the middle. It'll be essentially pure water. So if you did this right, and please don't do this, do not do this. You are not chemists. I do not trust you to do this without potentially hurting yourself. But technically, theoretically, you can take a strong acid, and if you neutralize it enough, you can turn it into pure water. It's going to have a little salt, right? Because the chemical reactions are going to happen, so it'll actually be probably more like a little salt water. But it could potentially happen just like that. So that's what this video is here if you guys want to go check that out. Now, we learned about our stomach acid being acid, but our blood is basic. So how does our body maintain where is acidic and where is basic? Well, it really uses these things called buffers to actually kind of buff the situation and prevent pH changes. So when you have an acid and you throw some base at it, it will shift on the the pH scale. We're done with the periodic table. It will shift on the pH scale, right? More closer towards the neutral, and then finally, if you keep adding base, towards the basic side. Now, your body has these things called buffers, and buffers go in there and they resist change to pH. So essentially, if you added a buffer to the solution, now you can keep throwing more OHs, but it's not going to change the pH. So essentially, you're taking that acid, you add a buffer to it, and now you're just pouring all that OHs in it. But it's not changing. The pH is not changing. That's what buffers do. They prevent a pH change. And that's because if you need to keep your blood basic, you need to keep your blood basic. So you need to add that buffer so that no matter what's coming out of your stomach, even if it's acidic, it's not going to change your blood concentration and stuff like that. And that's what basically maintains different pHs in our body, is these different buffers. So really cool and super helpful for not dying. Yeah, I'd kind of like to not die, so thanks, buffers. Now, sometimes I wish, certain places in our planet had buffers like our bodies, but they don't. One of those places is the ocean. So what happens is as we as humans pump out more CO2 than we're absorbing. So every breath you take, you're releasing CO2. Every time you drive your car, you're releasing CO2. Every time we do industry, we're releasing CO2. And that floats around in our environment until finally it gets absorbed in places like the ocean. Now, when it does, it actually goes through a chemical reaction and turns into bicarbonic acid, which is what is making our ocean acidic. So the more we drive around, the more we produce CO2, and especially when we're chopping down trees and stuff, because plants absorb CO2, but now there's less trees and more people, so now there's more CO2. The planet can't really handle it. It actually dumps it into the ocean. Well, it absorbs it, diffuses it into the ocean, and therefore it's creating what's called ocean acidification, meaning that more CO2 in the atmosphere means more bicarbonic acid, which gets created into the ocean, which means our oceans now are shifting pHs. And remember, pH changes can actually affect your proteins. That's true of marine animals as well. So now things are getting too acidic in the ocean, and that's actually causing lots of die-off, like coral reefs. If you've heard of coral bleaching, that's because of ocean acidification. It's actually a huge problem right now, and we're going to talk about that throughout the semester. but it really is a really big deal to decrease our CO2 emissions. And this is something that every single country on the planet has agreed that this is really important. This is what's causing things like climate change, is just our CO2 emissions. So we really, really need to keep an eye on this because it's causing things like our entire ocean to die. And guess what? Hate to break it to you, but trees are not the only way we get oxygen. In fact, like 70 or 80% of our oxygen comes from the ocean. So what happens if we kill everything in the ocean? We're essentially going to suffocate ourselves. So I'm not going to get into this now because we talk about this later on in the semester, but this is a big deal, guys. Think about this when you vote for your politicians and stuff like that, because there are people who are into this and who are like, yeah, we need to decrease our CO2 emissions. And then there are other people who are like, no, we need money. So the whole Paris Accord and the Paris agreements and stuff like that, it's basically a global agreement that says we're all going to reduce our CO2 emissions as much as we possibly can to save our planet. And every single country in the world, literally hundreds and hundreds and hundreds of countries have come together and said, yes, this is what we need to do. Except one. That is us. We pulled out a few years ago. So think about that in the upcoming election, guys. This is a big deal. We're essentially killing everything on the planet just because we're producing too much CO2. And these are things that we can easily, maybe not cheaply, but we can easily reduce and we can fix. And the planet is resilient. If we do it, you guys have seen, I'm sure, with all us locked inside, the reduction of the CO2 emissions. The fact that LA has had the cleanest air in like 40 years. The fact that you can see the Himalayas from India that you haven't been able to see in like 60 years because of the pollution, right? The planet is healing itself really quickly, and all it takes is just a little bit of our reduction of our carbon footprint. So anyway, I digress, but we will get back there because it's depressing. And it's not just that we're suffocating ourselves by losing the oxygen that we need, but chemically, this is affecting every single organism in the ocean, not just the coral reefs that are bleaching and dying, which is essentially like losing tropical rainforest. That's how much diversity is in these communities, right? This is, say, a shell from a mollusk. Think like the oysters that you eat, the clams that you might like. This is, I think, 45 days in acidic conditions. The shell is completely deteriorated. No, you like oysters, you like clams, gone, right? Things like crabs and lobsters also have these hard exoskeletons, gone, right? We're losing huge amounts of food if we lose our oceans as well. A lot of food comes from our ocean, guys. You don't even know. So anyway, I digress. But again, really, really important. CO2 creates these bicarbonic acids just by chemical reactions happening in our ocean because of too much CO2 emissions. So always really important to reduce as much as possible. All right, so with that, we get to our homework assignment. This is already up on the Canvas site for you guys. I have a link here if you guys need to go download it. It's also on the Canvas site. But this is due again after your first module, so make sure that you guys get this done. So make sure you check this out because this is talking about the dangers of dihydrogen monoxide. And remember, not all chemicals can be bad. For this one, I want you guys to do some research on your own and tell me, is dihydrogen monoxide bad, right? It might be. It's killing people. It might not be. I don't know. Go check it out. Anyway, thank you guys for another amazing lecture. I really appreciate it. I'll leave you guys with another terrible dad joke, as I like to do with the end of my lectures. And have a wonderful time, and I will see you guys for the next lecture very shortly.